Hey y'all, and welcome to today's lesson, which is lesson 32. We're starting module 6, which is all about the trig. This is lesson 32. We're going to talk about special right triangles today. But in order to be successful with this, I need to remind you how to simplify radicals. Okay, so the first step is if you have a radical, for example, we call this a radical because it's got the square root symbol, so this is a square root of 8. The first step is to get a list of factor pairs. So my choices are like 8 times 1, 4 times 2, right? So I'm going to use 4 and 2. And I'm going to list those down here, and that's where I put 4 times 2. And then what I notice is that 4 is a perfect square. So 4 can break down into 2 times 2, okay? And so that's why I'm going to take the square root of 4, which is 2, and that comes on the outside, and then I leave whatever's left behind. So the square root of 2 gets left behind in the radical. So let's do another one together. So if we're looking at the square root of 32, I'm going to, I know that it's 16 times 2, and then 16 I know is 4 times 4. So I'm going to, because it's a perfect square, the 16 is going to come out as 1 4, and the 2 is going to be left behind, because the square root of 16 is 4. So the square root of 72, again, I know this is 36 times 2. If I take the square root of 36, I get 6, and I'm left with 2 in the radical. And then 200, this is 100 times 2. And I know 100 is 10 times 10, so it will come out as 10, and the square root of 2 will be left behind. So I did that wrong on your paper. I don't know what I was thinking. Sorry. Down here, these would be all square roots of 3. So 12 is 4 times 3. So the 4 comes out as a 2, and the 3 gets left behind. 27 is 9 times 3. The 9 comes out as a 3, and the other 3 is left behind. And then 48 is 16 times 3. So the 16 comes out as a 4, and the square root of 3 stays behind. So obviously you can type these numbers in your calculator and get a decimal estimate of what they are. But this is what we call simplifying radicals. And this should bring you back to, I know I taught it in 8th grade. So next, today, like I said, we're going to apply this to learn special right triangles. So you may use either we're going to use graph paper to do this because not everybody has their technology and my iPads just don't work so good. So what I did for you was I drew 4 perfect as possible squares with one with segments of 2. So this square you can see has is a 2 by 2, and then we did one that's a 4 by 4. This one is a 6 by 6, and this one I actually made a mistake. Again, I don't know what I was thinking on your paper. So this should be an 8 by 8. So make sure I had somebody correct it for you. Please make sure that it's an 8 by 8 square by counting the sides. All right, so that's where we are here. Then we've gone ahead and drawn a single diagonal. Remember, a diagonal connects two opposite angles. And we leave the other one empty. And what you should notice here is that this empty square has a right angle, so it's a right angle, but then we also know that these two sides are congruent, so that means that these two angles are congruent, so that means it's also isosceles. This is not an equilateral, but it is a right isosceles because we have a right angle and two equal sides and 2 equal, and we'll call them base angles. So now we've established that the half-square triangles were right isosceles triangles. Now we want to know what are the measures of the acute angles. Okay, so you could use a protractor to measure these, but what else we can notice is that this whole angle is going to be 90 degrees, and we're looking at just half of it. So each half is going to have to be 45 degrees, because 45 plus 45 equals 90. And then we'll notice an exact repeat of that down here. This is cut in half, so this angle is 45, and this angle here is 45. And that should be the case for every one of these triangles. That the little angle is 45 degrees. And so what we've made is an isosceles triangle with 190 and 245. And we can test, because if we do 90 plus 45 plus 45, you do in fact come up with 180 degrees. So each of our isosceles triangles is 180 degrees. Another thing you could do is you could fold the triangle along its diagonal, and if you reflect it along the diagonal, you should also notice that it lands on itself. So we can prove that these triangles are congruent several different ways. We could use, we know these sides are congruent, and we know this angle is congruent to this angle, so we could use side angle side. You could say that these sides are congruent, but we also know that this side's congruent, so that would be side, side, side. So there's several different ways to go about proving that these triangles are congruent. All right, so now that we know that they're right triangles, we can use the Pythagorean theorem to find the length of the diagonal. All right, so let's look at the 2 centimeters by 2 centimeters, and we're looking for this diagonal here. So basically we're saying a squared plus b squared equals c squared. And we know a and b are the same, so it'd be 2 squared plus 2 squared equals, well, this is 2, that's 4 plus 4, which is 8. And the last step is to take the square root of 8. Okay? So one way we could do this is we could put this into a decimal, and we would get the solution. But because we want to keep it in reduced radical form, which is a simplified radical, and you should have this from the beginning of class, the square root of 8 breaks down into 4 and 2. So the 4 comes out as a 2, and the square root of 2 is left behind. So in your table, you're going to say a square that's 2 centimeters with a leg length of 2 has a diagonal or a hypotenuse of 2 square roots of 2. And then we'll do the same thing for the side lengths of 4. So I know that this has a side length of 4, and this has a side length of 4 in the second observation. And then we're going to see if we can come up with a pattern. 4 squared plus 4 squared equals the square root of, well, this is 16 plus 16, so it's the square root of 32. And again, we remember that 16 times 2, so that comes out as 4 square roots of 2. So when the square has a side length of 4, the leg length of the right triangle is 4, and the diagonal of the hypotenuse is 4 square roots of 2. What you should find if you do the same thing for 6, when the leg length is 6, the diagonal or the hypotenuse is 6 square roots of 2. And when it's 8, you'll find out that the diagonal is 8 square roots of 2. So what can we conclude? Well, what we've just discovered is that when you have a 45-45 triangle, so that means you got one right angle, and the two base angles are 45. We know that the two sides are going to be A. They're going to be equal. And then we know the hypotenuse is going to be whatever that side length is times the square root of 2. And we noticed that when we did our chart here. If the leg length was 2, the diagonal was 2 times the square root of 2. If the leg length was 4, it was 4 times the square root of 2. And that will always be the case when you have a 45, 45, 90. All right, let's look at a 30, 60, 90. Okay, a 30, 60, 90 is going to involve equilateral triangles. Okay, so what do we know about an equilateral triangle? Well, that's all the sides are equal. So what I did was I made a 2 by 2 by 2, and a 4 by 4 by 4, and a 6 by 6 by 6, and an 8 by 8 by 8. And what do we know about all the angles in the equilateral triangle? Well, they're all 60 degrees. So this would be 60, this is 60, and this is also 60. Okay? So that's our knowledge of an equilateral. All angles are 60 degrees. It doesn't matter which one you're looking at. Incidentally, these are all similar triangles. All right, now we're going to go ahead and block out one of the triangles. We're going to draw a altitude is what we call this down here, and we're going to block out one side. And now we're going to see what the relationship is between the other sides. Okay, so one thing we know is that when we draw an altitude, this is going to make yet another right triangle. So these are all right triangles here on this side. Another thing we know is that this angle right here is 60 degrees because in all these angles, this one's 60, 60. Because we did have all three angles being 60 degrees, but now we know that for sure this angle is 60 degrees. We know this angle is a right angle, and then we know that this one was cut in half. It originally was 60, so that means this is going to be 30 degrees, and this is going to be 30 degrees. So now we've got a 30, 60, 90 that we're looking at. And let's look at the special relationships in it. Okay. So we know they're equilateral triangles. We know that when you cut an altitude down the middle, you have now created two equal triangles. And you can prove that by SSS, SAS, hypotenuse leg, all the different ways of proving that. So now let's go ahead and look at each half equilateral triangle and try to come up with the length of the hypotenuse. So for the first one, we know that this side is going to be 1, 1, and we know these two sides are 2. So this is 2, 2, and this would be 4. Okay. So this side is 3, but we know from the original that this was 6. And then if we're looking at just half of this, 4 and 8. Okay, so in this case, we now have a leg and a hypotenuse. All right, so now we have a leg and a hypotenuse in each of these. So we're going to do some subtraction to figure out the solution. So for the first one, we're looking at the triangle is equilateral 2 by 2 by 2. So the longer leg is going to be the leg across from the 60 degree angle. So in this case, it would be the X in all cases. All right, so we'll just call it X. And the shorter leg in this case is going to be 2. And the hypotenuse we know is also, I'm sorry, the shorter leg, my bad, is 1. And then the hypotenuse is 2. So if we wanted to find out the longer leg, we would do 2 squared minus 1 squared, because we know a squared plus b squared equals c squared. But in this case, we have c and we have, say, a. So we're going to do c squared minus a squared to give us b squared. And we'll say that the longer leg is b. Okay, so you're going to do that for each one. And you'll get that the longer leg in this case, well, this is 4 minus 1, which is the square root of 3. In the second triangle, you've got, you don't know the longer leg, you know the short leg is 2, and you know the hypotenuse is 4. This is 3, 6, and this is 4, 8. Okay? So in the second case, you're going to do 4 squared minus 2 squared, which equals 16 minus 4, which is the square root of 12. And earlier we learned that that would be 2 square root of 3. And then we're going to do 6 squared minus 3 squared, which is 30.